In this video, we'll discuss the formation of action potential. Action potential is the membrane potential of axon when conducting impulse. During action potential, the axon will change from polar state that we call resting potential to depolarization state, and then repolarization state, and finally hyperpolarization state. During depolarization, the inside of the axon will become more and more positive up until the maximum value of plus 35 mV. After depolarization, the membrane potential on the inside of the axon will slowly become more negative, which is becoming less than the plus 35 mV, moving towards the initial minus 75 mV. This is why it is called repolarization. Next, following repolarization, the axon membrane will undergo hyperpolarization, where the inside of the axon become even more negative than the minus 70 mV. The changes in the membrane potential during depolarization, repolarization, and hyperpolarization is called action potential. First, we will discuss the sequence of events involved during depolarization stage of the action potential. It starts with stimulus triggers opening of some of the voltage-gated sodium ion channel found on the axon membrane. Sodium ion then enter the axon down concentration gradient. The concentration gradient was previously established during resting potential. Because of the concentration gradient, this is why sodium ion move into the axon and not move out of the axon. As a result, the inside of the axon will become more and more positive as the sodium ion concentration increases. At this point, the membrane potential is no longer at minus 70 mV, meaning that the membrane is no longer polar. This is why it is called depolarization. The amount of depolarization triggered by the stimulus depends on the strength of the stimulus. Stronger stimulus will lead to higher value of depolarization. If the initial depolarization caused by the stimulus achieves the value of minus 55 mV, this will trigger opening of most voltage-gated sodium ion channel. More sodium ion will diffuse into the axon down their concentration gradient and causes the inside of the axon to become even more positively charged. The membrane potential value will increase from minus 55 mV up until plus 35 mV. This is called the rising phase of action potential. At this point, because of depolarization, the inside of the axon now has high concentration of potassium ion and high concentration of sodium ion. When the inside of the axons becomes more positive compared to the outside of the axon, this will trigger the closing of the voltage-gated sodium ion channel and opening of the voltage-gated potassium ion channel. Next is repolarization, which occurs directly after depolarization. It starts when the potassium ion diffuse out of the axon down their concentration gradient due to opening of the voltage-gated potassium ion channel. Diffusion of potassium ion out of the axon will cause the inside of the axon to become less positive, heading towards the minus 70 mV value. This is why it is called repolarization, because the value of the membrane potential is moving towards the polar state. However, upon reaching the minus 70 mV, potassium ion still continues to diffuse out of the axon, which causes the axon to become even more negative than the resting potential value. At this point, hyperpolarization has occurred. Excess loss of potassium ion from the axon is due to some of the voltage-gated potassium ion channel still open after the membrane potential value has reached the minus 70 mV. In this example, we can see that the membrane potential value has become even more negative than the minus 70, which is minus 80 mV. Once all the voltage-gated potassium ion channel have closed, only then the value of the memory potential will return to resting potential. After the action potential has completed, the memory potential of the axon will once again become resting potential. The inside of the axon will become more negative, while the outside of the axon will become more positive. However, notice that because of action potential, the outside of the axon now have higher concentration of potassium ion, while the inside of the axon now have higher concentration of sodium ion. This is where the sodium-potassium pump will restore the concentration of sodium ion and potassium ion across the membrane back to original state during resting potential, where higher concentration of sodium ion is on the outside while higher concentration of potassium ion is on the inside of the axon.